I'm just making a very brief presentation of this nice paper that looks at how to trap CO2 in the mechanochemical processing of rocks, which happens. A lot of rocks get crushed for building, for construction material every year, and the idea here is that there are processes by which CO2 gets trapped in those rocks, silicate rocks, is different than what was thought before. And if the crushing happens in a CO2 rich environment where the CO2 is a byproduct from somewhere else, then there is potential for sequestering CO2 into it. Now imagine that you are also making cement that can trap and keep CO2. Before making cement, you are producing material that's also trapping CO2. So these are small contributions, but nonetheless they may become part of the overall portfolio towards decarbonizing the system and heading to net zero by the 2050. Yes, 2050, right? I'll just read some text. I won't go into the figures, which are basically based on their experiments of crushing rocks, leaching minerals, and then also decarbonizing or extracting the materials out of them to measure how they do at various temperatures in terms of desorbing the calcium and CO2 that's in the material in the rocks. Milling minerals rich in magnesium and iron within CO2 gas has been proposed to capture carbon as metal carbonates. We conduct milling experiments in CO2 and show that polymineralic rocks such as granite and basalt, whether high or low in carbonate forming metals, are more efficient at trapping CO2 than individual minerals. This is because the trapping process is not, as previously thought, based on carbonation of carbonate forming metals. Instead, CO2 is chemically adsorbed onto crystal structure, predominantly at the boundaries between different minerals. Leaching experiments on the milled mineral rock powders show that CO2 trapped in single minerals is mainly soluble, whereas CO2 trapped in polymineralic rocks is not. Under ambient temperature conditions, polymineralic rocks can capture greater than 13.4 milligrams CO2 per gram as thermally stable insoluble CO2. Polymineralic rocks are crushed worldwide to produce construction aggregate. If crushing processes could be conducted within a stream of effluent CO2 as byproduct from cement manufacture, for example, our findings suggest that for every 100 million tons of hard rock aggregates sold, 0.4 to 0.5 million tons of CO2 could be captured as a byproduct. So you can see that if you take the total amount of hard rock aggregates being produced, then the amount of locked up CO2 can go up quite nicely as just a co-benefit of the great demand for CO2 that's expected to continue, especially for countries like China and India, which are building infrastructure and buildings at a very rapid rate to keep up their economic development and the needs that go along with those. So these are the experiments looking at basalt, granite, and other types of rocks. We talked about olivine a lot in enhanced weathering, for example, so I won't go into the detail. Carbon captured by mineral composition, again you can see the numbers for basalt, granite predicted, and basalt predicted, granite predicted. There are some details on how the X-ray diffraction are used to look at these CO2 trapping and so on and so forth. And then you release what is adsorbed, for example, to look at the temperature sensitivities of these various CO2 capturing they do. So looking at counts per second in hundreds of thousands and temperatures at which various minerals are producing the CO2 trapping is looked at. So I'm skipping the results because this is not such a big contribution, but it's an important contribution and an important co-benefit of cement production, which remains a very dirty product dirty industrial process. We have talked about cleaning up the cement and steel industries elsewhere, so this is just as a little addition to that. In the discussion, they say we propose the following mechanism for mechanochemical trapping of CO2. Mechanical activation deforms the crystal lattice, preferentially at the boundaries between different minerals. This is where polymineralic rocks play a good critical role. When a mineral is deformed, dislocation in the crystal lattice migrate to the mineral surface, generating charged species. If bonds break during fracturing, a localized instantaneous temperature rise occurs, surface radicals form, and charged silica and oxygen become available. We propose that both surface radicals and charged species lower the activation energy required for CO2 chemical absorption to the surface and promote diffusion of CO2 into crystal lattice interstitials. Very different than the carbonation process. The resulting bonds between the CO2 and the charged mineral surfaces are extremely strong, meaning that the absorbed CO2 is relatively insoluble. Our results indicate that the presence of CO2 in the lattice weakens the bonds holding some ions in the lattice, thereby releasing more calcium and magnesium into solution during leaching, the process that happens when the rocks come in contact with water, for example. When reacted with water, the weakened bonds are easily broken. Thus, in the polymineralic rocks, more calcium and magnesium ions are dissolved into solution. Serendipitously, this increase in the leaching of calcium and magnesium provides additional CO2 trapping potential in the form of aqueous carbonate precipitation, kind of a leaching of CO2 into carbonate minerals. Our research shows that during mechanochemical CO2 trapping experiments, polymineralic rocks outperform individual minerals in terms of both the amount of CO2 captured and the subsequent leachability, making them viable substrates for carbon capture and future study. Experiments conducted in ambient temperature conditions show that basalt and granite can trap 15.4 milligram CO2 per gram and 13.9 milligram CO2 per gram respectively when dry milled in gaseous CO2. So to basically increase CO2 in the environment where they are being crushed. We demonstrate through XRD, X-ray diffraction analysis and thermal desorption that the mechanism for mechanochemical trapping of CO2 in rocks and minerals is not as previously thought in the form of carbonate mineral production. Rather, our experiments suggest that mechanochemical trapping occurs via chemical absorption of carbon within the mineral lattice, which preferentially occurs on grain boundaries. A comparison of carbon trapping in polymineralic systems like basalt and granite with that trapped in pure mineral systems shows that polymineralic rocks trap significantly more CO2 than would be expected from their mineral composition. We show that mafic minerals previously proposed as mechanochemical substrates leach 60 to 93% of their trapped carbon when mixed with water. So soluble CO2 gets re-released. By contrast, the CO2 trapped in polymineralic rocks is poorly soluble, with 2% leached from the basalt and 4% from the granite. Hence, the resulting materials form a usable and resilient product to put away CO2. Based on our finding, for every 100 million ton of saleable hard rock aggregate, 0.4 to 0.5 million tons of CO2 could be trapped into quarry fines as a byproduct of existing global aggregate production. So this is the key point, that these aggregates are being produced in massive quantities. Sorry about the camera there. But this process of mechanochemical trapping into polymineralic rocks offers a new way to trap CO2 into the aggregates that are being produced. Okay, let me leave it here.